This is Lab 4 Oscillations. So the purpose of this lab is to compare the predicted versus observed motion of mass attached to a spring. We plot the change in energy of gravity, kinetic, and spring when overall energy is 0. For our models, the system at first is mass and the surroundings is earth and spring, and then for the energy part of it, our system is mass, spring, and earth, and then nothing is the surroundings. Our fundamental principles are Newton's second law, the momentum principle, gravitational force, energy principle, and spring force. So this is Newton's second law, force equals mass times acceleration. From this, we get the position update formula and velocity update formula. Position is final position equals initial position plus v average change in t, and v average is initial plus final divided by 2. And then the velocity update formula is final equals initial plus net force divided by mass times delta t. And then our gravitational force and energy are here, so our potential energy of gravity is mgy hat, and then our force of gravity is negative mgy hat. Mass in this case is 0.402 kilograms, gravity is 9.8, and y hat is just the positioning vector that it is. The energy principle is the energy of the system equals the work from the surroundings plus Q, which is heat. Kinetic energy is, the change in kinetic energy is 1/2 mv squared. For spring force, we have negative K times S L hat, and S is the change in position of the spring from relaxed length to not, and then L hat is L divided by the magnitude of L, and then L is the position minus the fixed position. And that goes along with the potential energy of spring force, which is 1/2 K S squared. So for our intro, we have a tracker video, our models, and our graphs. Our findings are that the model is good at predicting the positions of both x and y. It's fairly good at it, and that all of the all other change in energies sum to 0 when everything is the system, as we can see here. So this is our tracker video. So I just tracked the positions in the x and y of this. The initial conditions came from the pre-lecture video. We got that the calibration length was 0.7 meters. The time between frames is 10.5 seconds. Origin at fixed, or the origin is at the fixed end of the spring. So these are initial conditions, and this is the graph that we get. This is the x position, this is the y positions. These data here, the x and y, is what we put into the code to get the graphs and all that. So our initial code calculations, this is from the pre-lecture video. The ball's mass is 0.402 kilograms. Our ball's position vector, we first start at the negative x area and negative y area. We just put those in there. Initial velocity is 0. Delta t and t we don't change, and then gravity is 9.8. So our Ks for this we got from the video again is 6.83 newtons, and our relaxed length is 0.123 meters. And then this here is L hat and S, which I'll explain on the next slide. So now we have for spring, the force of spring and the force of gravity. Gravity vector is over here, mgy hat. So the ball's negative, ball's mass times gravity, and then spring is negative KSL hat. And then F net, as we can see over here, force of spring goes up, gravity is down, so gravity can be greater in some situations, or in this situation it is, and it's just the sum of both of those. So we know that F net is F gravity plus F of spring, and then we use our position update formulas to get ball's velocity and ball's position, and then L hat, L, and S we find from over here. I explained it earlier, and yeah. So then we have to do our calculations for energy. So note this time the system is the earth, mass, and spring, and then there's nothing for the surroundings. So using our energy principle, E equals work plus Q. There's no Q here, and so everything is just work of the system, which is everything. So we have change in kinetic energy, change in potential gravity energy, and change in potential spring, which are these equations here. So we just plug those into here, and then energy, or total energy, equals K, potential gravity, potential mass. And this should be 0 because there is nothing in our surroundings. And then to find delta K, delta G, delta S, we just final minus initial for each one of those. So these are our results. So the blue is the code model, and then red is from the tracker data. And as we can see, both models are pretty good at predicting positions of the mass in x and y positions. Our errors of discrepancy is most likely due to not keeping the center of mass constant in the tracker video, and like just the video being maybe not the best quality. There also could be some drag force. I'm not really sure, but it's pretty minimal discrepancy, so it's probably just the center of mass. And then for our energy components, we see that a change in gravity and spring oscillate between each other, and then we have kinetic energy has a low magnitude, but most importantly we see that delta E is 0, which is exactly what we want. And then errors that account for that are probably not accounting for other energies such as thermal or rotational, but it's 0. So okay, so what does it mean? Is the energy principle satisfied? Yes, it is, because our system is nothing. This is 0, so everything, and we aren't working with heat, so everything's working with work, and we can see that energy is constant at 0, so total energy is 0, which is good, and so it is in fact satisfied. And then making preparations for or finding oscillation. We can find periods of oscillations from the average of each cycle. Each cycle is at a trough, that's at the lowest point. I'm just going to do 3 of them and take the average of that. So the estimated for x is this value right here. The estimated for y is this value right here. The difference is 0.095, which doesn't seem like a lot, but it kind of can make a few big adjustments on spring force, the K constant, spring potential energy. As you see up here, this is T, and K is related in this way, so having a different T is going to change our constant of K, which would then go into changing our spring force values and our spring potential energy values. And the errors for this are most likely due to inconsistencies in tracking the center of mass on tracker. But yeah.